Okay, hi everyone. Welcome to another Slam Talk. This week, Ashok Vardhan is gonna tell us about attention with Markov, a Markovian tale of transformers. Um, Ashok is a postdoc at EPFL and an incoming faculty at Telecom Paris. Thank you.
Thank you. Thank you, Anis, for the kind introduction and the invitation. Just 1 second before so today I'll be talking about my recent body of work titled Attention with Marco, and this is in joint collaboration with many wonderful colleagues at like Berkeley, MIT, EPFL, and UT Austin. So, yeah, let's get started. So, as you see, the title has like two keywords, important ones, the attention and Marco. So, what exactly is attention? So yeah, it is exactly what you expect it to be. It's a mechanism that the heart of many foundational language models, like many of your favorite ones, right? And on the other hand, Marco refers to the legendary probabilist whose eponymous process at the heart of many probabilistic modeling. So how exactly these two are connected? So let's find out in today's talk. So before we get started, as you know, this is like the customary prayer to LLMs in every talk. uh, so the models occupy a very integral part of our daily lives, and so much so forth that we spend an innumerable amount of time with these models, right, on a daily basis. But at the same time, as with everything in life, there are like both aspects to it. On one hand, we see these models behaving like sometimes like literary geniuses, but at the same time struggling on some of the like the most basic arithmetic tasks and so forth. And with more and more critical integration of these models into many of these critical sectors, right, there is a critical need at the moment in order to understand what exactly these models do, and in particular how exactly do they learn. So this kind of fundamental understanding is very important, and in order to do that, we need principled frameworks and tools that enable this understanding, right? uh, while okay, you can say that this is a very wonderful goal to have, but at the same time there are many inherent challenges to this setting, right? Because uh, these models are like by default very complex, and at the same time making any tractable analysis of these models mathematically fundamentally impossible, right? There's like some of the two key challenges we have to grapple with, and that's exactly where my research comes in particular for a popular class of widely used foundational models called transformers, leveraging classical fields of information theory and statistics. I design principal frameworks and tools that enable a tractable analysis and understanding these models, and that's exactly what the framework is called attention with Markov. Okay, and the main idea behind this framework is that if you take a look at the current pipeline for how these models are trained, most often it's on sequential inputs, right? So the main idea here is to replace this sequential inputs with specifically Markovian structured inputs. Okay, and once we do that, this allows us for like a fine-grained interplay where on the input side you can change the memory or the order of your Markovian process, and on the model side you can tinker around with the depth, and this kind of interplay will give us a very richer and tractable understanding to address these questions, in particular what exactly do these models learn, and in particular how do they learn them. Okay, so that's exactly what our framework enables us to do. Using this framework, we very precisely address these questions. Okay, so this is like the overall overview of what this framework does. Okay, and the main takeaways emanating from this body of work are we show that depth of the model actually plays a very critical role in the transformer functionality, and then surprisingly, even one layer models can fail on the simplest first order Markov chains provably, but at the same time, even more surprisingly, it turns out that no matter what your Markovian order is, just a three-layer transformer can suffice to learn it. Okay, so these are the main key insights emanating from this framework, and the key takeaways for today's talk as well. Okay, and this talk is based upon this following three set of works that appeared at New Rips and Dissler, and I would be happy to send these papers offline as well. Okay. Yeah, so coming back to our framework, as I was saying, on the input, you can tinker the memory, and on the model side, depth is like the tunable knob, and you can ask why specifically are we considering Markovian structured inputs, right? If you take a look at languages, right, they have a lot of inherent structure, starting like grammar, syntax, and so forth. But at the same time, they also exhibit to some extent Markovianity, meaning if you know like the past few words in a sentence with a reasonable accuracy, you can predict the next one. And similar, like past few alphabets in a word, you can predict the next one with a reasonable accuracy. And this kind of uh, Markovian, what do you say, lens to understand models actually goes all the way back to Shannon in his groundbreaking work on information theory. Okay, so this is like the main motivation behind why we consider Markovian structured inputs. Okay, so just a note I want to add here. So we are not claiming that languages are just Markovian. Okay, no, definitely not. They have even more structures, but this is one tractable, structure that will enable us to get to the heart of how these models work. Okay, so that's like the motivation why we are considering Markovian inputs. And today's talk, so this is like the outlines. In the first part of the talk, where I'll spend most of the time, I will consider uh, like the simplest setting of first order Markov chains, memory one, and single layer transformers, okay, depth one. And then in the second part, we let the memory to be arbitrary and consider depth greater than one transformer. So this covers the full, spectrum of the possible combinations here, which will give us a very detailed picture of how the, learning happens in this scenario. Okay, so that's the outline. So let's get started with part one. Okay. Uh, so what exactly are first order or memory one Markovian inputs? Okay, so here we consider binary Markov chains without a subset. Okay, yeah, we can consider finite state, but let's start with the binary state Markov chains. So as a first order Markov chain, as you know, you can be represented. So it can be represented using a simple state transition diagram. There are like two states, 0 and 1, and you flip with probability p here, and 1 to 0 with probability q. Okay, mathematically precisely also you can write it as like a, there is a transition matrix, right? P corresponding to these probabilities, 1 minus p, p, q, 1 minus q, that you see, and starting with some stationary distribution, right, which is easy to compute in this scenario. But the main thing to take away is, yeah, just this picture is enough, right? There are two states and you're flipping with these probabilities. And the key quantity that I want you to remember for this talk is this term p plus q. So as you see here, p plus q refers to the total switching probability, right? With p, it flips from 0 to 1, with q, the other way around. So p plus q roughly captures the, the proneness to switching. Okay, this is the term that I call switching factor. Okay, this is the main thing that I want you to remember from this part. Okay, so this is a first order Markov chain, which we saw. So now let's take a look at transformers architecture. Okay, so what exactly are transformers? Okay, sorry. Yeah, this is too complex for us. Yeah, this is even more complex. Yeah, so these are like the class of sequence to sequence models, right? Given a sequence of inputs, you predict the next token prediction probabilities using this architecture where there are various components. This is just to give you an overview. Okay, I mean, you don't need to worry too many details about this. There is like an embedding layer upon which you pass them through a attention layer, which is at the heart of these models. Then you pass it through feed forward, linear layer, and so forth, right? That's how you get the prediction probability. So they're saying the core mechanism of these models is attention mechanism, where at any time instant you attend to all the past tokens in a causal manner. Okay, that's the core functionality of these models. And more mathematically, this is how the set of equations look like. I'll just give a very rough overview. I mean, you don't need to worry too much about what exact symbols mean. The main idea, as I was saying, embedding is given a token, right? Here in this case, binary. You embed it into some high dimensional embedding and you add a positional embedding. Then you get xn, and at each for each embedding xn, once you pass it to the attention layer, you compute the yn as some past weighted combination of the embeddings and, yeah, the current one using skip connection. Then you pass it through this yn through a feed forward, like a one layer ReLU, you get a zn. Okay, and then finally you project the zn into some real number, right? Because in this case, as I was saying, there are but it's a binary alphabet, so it suffices to have just one real logit. That's what you get here. And then finally you compute the prediction probability here, which you see as f theta. So this means at any position n, when you have the input sequence x1 to n, the next token prediction probability, which is in this case p theta of xn plus 1 equals to 1, right? Given the conditional past, it is computed as sigmoid of this logic. Okay, this is just the full overflow of the single layer transformer. So as I was saying, the key core components are this attention here, and finally the prediction mechanism where you compute the prediction probability. Okay, so this is a single layer transformer, and so theta here denotes all the set of matrices, okay, jointly, like weight matrices, embeddings, everything, all the set of parameters. I'm denoting it as theta. And here, so we consider two scenarios which you might all be familiar with. One is called weight tying. So there's a popular uh, uh, practical choice people employ for many of these models is that they use the same set of weights for both linear and embedding. Okay, just the transpose of each other, which is called weight tying. Okay, so we consider this scenario and also the general scenario where they're independent and they can be arbitrary. Okay, that's the no weight tying. And yeah, together, so we have seen what the architecture of a single layer transformer is. So put together, so on the input, you have the data generated from a first order Markov chain. Sorry. Then, yeah, you feed it to a single layer transformer, this x1 to x capital N, and then the model predicts the next token probabilities denoted by these f thetas. Okay, so this is overall the input and the model, yeah, viewed together. Okay, but that's not the end of the story, right? These models need to be trained on suitable laws. So here we consider the next token prediction laws, whose expression is given by the following. So it might look fancy, but it's nothing but, as you know, the cross entropy loss between the next token xn plus 1 and the current prediction probability, which we know as f theta of some x1 to n. Okay, this is the negative log likelihood, also the cross entropy loss. So in an ideal scenario, you can ask, is this loss any good, right? Like, why do we consider this loss? It turns out that yes, like in an ideal scenario, when does this loss get absolutely minimized is when the prediction probability f theta exactly matches the Markov conditional kernel. So as you see here on the right hand side, the conditional probability only depends on the last token. Why? Because it's a first order Markov chain, right? So it suffices to just consider the last token. So on the left hand side, in principle, the model could utilize the full pass f theta x1 to n. So here, in the process of training the model on this loss, the hope is that the prediction probability uh, matches the Markov kernel. So basically, the model has to figure out that it need not use the full pass, but it just needs to use the last immediate token. So that's like the hope through using this loss. But does it happen exactly like that in practice? Uh, Unfortunately not. It turns out that you can probably show that in this setting, models can probably fail to learn even on first order Markov chains. Okay, and how exactly does this happen? This is just to give a rough overview. You can show that under certain scenarios, the model can get stuck at some local minima. Though there are a global minima corresponding to this Markov kernel, sometimes you can get stuck. And surprisingly, if you change some configurations in this framework, turns out that the model can escape these same points because they turn out to be saddle points and can principally go to this global minima. Okay, so this is like the overall rough overview of how the results look like here. So now getting into more details. So if you have weight tying, it turns out that the loss landscape roughly looks like the following, where first of all, to begin with, there are always global minima on this, meaning there always exists a realization theta parameters is denoted by theta star, so that the prediction probability exactly matches the Markov kernel, which is good. Okay, that means the loss is, yeah, a good loss surface. You can always realize the Markov kernel, and you can show that these points are global minima. Okay, but this is not the interesting aspect. The interesting aspect is that you can show that if your switching is greater than 1, there exists some bad local minimum on the loss surface where the prediction probability f theta pi is exactly the marginal. Okay, so let's take a moment to parse this. So you see on the right hand side, marginal doesn't depend on anything, it's just something constant, whereas left hand side in principle could depend on the full pass sequence. So it turns out, so what it means is that the model is just estimating some constant probability at each position, which is the probability of symbol being 1, which is just the marginal. Okay, and you can show that these kind of points are bad local minima, which exactly appear when p plus q is greater than 1. Okay, that's like the main result, one main result. And the moment you remove weight tying, interestingly, it turns out that the same point that we had before now turns out to be a saddle point. Okay, satisfying all the same other properties. Okay, so in principle, if yeah, the algorithm could escape and go to global minima if it touches this point. Okay, so that's like the rough idea. And more concretely, theoretically, we show that, okay, if your switching is greater than 1 and if you have like a weight tying, we saw that there are like explicit constructions of your parameters so that it's a theta pi, which is like a bad local minima for your loss, meaning your loss is strictly greater. It's a stationary point. Okay, that's the last thing. And you can show that the prediction is exactly the marginal and the loss matches like entropy of some stationary distribution. Okay, so this is like the first main theoretical result we have. And the moment you remove weight tying, it turns out that the same point that we had as before uh, becomes a saddle point now. So theta pi is now a saddle point and the rest of the properties are the same. So these are like the two main concrete theoretical results that we show here. Okay. And the main intuition behind this result, how we go about showing this is that, so if you take a look at the architecture, right, especially at the linear layer, if you put the the weight parameter here a as 0, we can see that the logit is a constant, right? It will be just the bias. So the prediction probability is sigmoid of this bias, and it's you can find the appropriate parameter so that it matches just a marginal pi 1. Okay, so you can realize the parameter so that you ignore the full sequence, whereas it just matches the marginal. Okay, and one could show that such kind of parametric realizations under weight tying, if you compute the Hessian, it turns out to be like almost positive definite, using which you can show that it behaves like a local minima, whereas if you don't have weight tying, this Hessian becomes like indefinite, implying that it's a saddle point. Okay, so that's like the rough intuition about how we go about showing these things. Okay, yeah, so this is like the overall picture. If you have weight tying, show that there are some explicitly bad local minima, whereas if you remove weight tying, yeah, the same point turns out to be saddle point, uh, provided your switching is greater than 1. Okay, so you can say, okay, so far this is like, okay, maybe a set of theoretical results about, okay, what, I don't know, like, yeah, this could happen, that could happen, because so far I only showed you that, yeah, these are the points that could exist on the law surface. So you can say, okay, maybe this is just a theoretical esoteric landscape, but that's not exactly the scenario. In practice, that's what exactly happens. We see here that, the first dotted line is the entropy. It's called it here. It's written as entropy of stationary distribution, right? That's like the uh, local minima loss surface, whereas the entropy rate is like the global loss value. When you have weight tying, we see that like the model gets stuck at this local loss surface, right? The red curve, whereas the moment you remove weight tying, we see that immediately it escapes it and it goes to the global minimum. Okay, so this is what we empirically observe as well, which in fact has been the main motivation for our analysis. Okay, so this is the yeah, uh, exactly what happens in practice. So to conclude in this setting, so this is like the main picture that I want you to remember is, as I was saying, yeah, in the presence of weight tying, the model gets stuck at some bad local minima, and whereas in without weight tying, it potentially escapes its saddle points to go to the global minimum. Okay, so that's like the overall, overview of what happens if you have first order Markov chains and single layer transformers. Okay, so far what I presented only covers one aspect of this, uh, the questions, right? Like particular, what do these models learn that we saw, but it's equally also important to learn how exactly this phenomena happen, right? Uh, the dynamic landscape. So to do that, we study the learning dynamics, okay, of these models. In particular, we'll focus on gradient flow. Okay. So what exactly is gradient flow? So as the name suggests, so the flow is nothing but the time derivative of parameters equals the negative gradient of your loss. Okay, so theta t denotes your all the set of transformer parameters. If you recall, L is your next token prediction loss. Okay, so here going back to the transformer architecture, as I said before, sorry, theta denotes all the set of transformer parameters, right? Embeddings, everything, these weight matrices and so forth. So it's a very interesting phenomena that we observe empirically is that when you train these singular transformers on this, it turns out that all these matrices that you see, W's, everything, they all turn out to be like exactly rank one. Okay, it's like a very surprising phenomena. We don't know why that happens, but that's a empirical fact. Turns out that they all like exactly rank one, meaning yeah, these embeddings and positional embeddings, they lie in some directional vector, and this directional vector is like the eigenvector for all these matrices. And using this observation, it turns out that it suffices to just consider, instead of these matrices and this all these vectors, it suffices to just consider three scalar parameters, which basically denotes the scale along this low rank component. Okay, that's like the main idea. So with which it turns out that instead of studying this full set of matrices, it suffices to study just the evolution of these three scalar parameters here. E denotes the embedding scalar. Okay, A denotes the attention scalar. W denotes like the weight scalar for the these weight matrices. And now with this reparameterization, we just have, yeah, theta in R3. So basically we reduce the dimension drastically just to three-dimensional Euclidean. And this is all thanks to, you can say, yeah, very curious phenomena that happens, especially for this setting, which is being rank one. So we are making use of this empirical fact that finally they exhibit rank one. So we are considering this reparameterization structure to study the flow analysis. Okay. Oh yeah, any questions so far? Or do we ask, we ask in the end?
I think it's all good for now. Thank you.
Okay, okay, perfect. So with this reparameterization, now we have the flow as, yeah, it's a Euclidean flow now in a three-dimensional Euclidean space, theta t, right? Et, Wt, and At. So, so natural question now is to ask, how does this flow look like, right? Now that we have vastly reduced the problem. So to address this, what we do is first let's consider that there are only two parameters, okay? So that it's easy to visualize. And also in this case, it turns out that this is good enough because the attention turns out to be 0. But let's to begin with, let's say A is 0, okay? Attention is 0. Then you have only two scalar parameters, E and W. That's your theta. So how does the flow look like now? So this is exactly how the phase portrait looks like for the flow when P plus Q is less than 1. So let's take a moment to parse. So here, as you see here on this picture, the set of all global minima are this, these purple curves, okay, the two of them, and the set of all local minima, this is red line on the x-axis, whereas on the right side, the blue line is the set of all local maxima, the middle being the intersection being the saddle point. So as you see here, all these flow arrows nicely nicely follow specific curves, some set of curves. So these are nothing but contours of some like an energy function. So it turns out that for this setting you can write an energy function which is like a conserved quantity under the flow. That's why this flow directions follow this constant energy surface. So that's like the overall idea. Okay, and the main takeaway here is that this flow can also be visualized as the following into these two set of green regions and red region. So what this means is that if you initialize anywhere in this green region, okay, the flow eventually takes you to the global, to a global minima. Okay, so that's what the green region does, denoted by I star. Whereas if you initialize it in the red region, you always get stuck at local minima in the end. Okay, so now as you see here, typically as we do like generally Gaussian initialization, right, with the zero mean. So that means you're initializing around origin. You see that when P plus Q is less than 1, the flow takes you to global minima. Okay, so that's actually one of the reason why in our experiments before, we didn't observe any abnormalities for p plus q less than 1 is because of this, this because of this region, because this under standard initialization, you end up in global minima more so than local minima. Okay. Whereas if you change the switching factor to p plus q greater than 1, turns out that the phase portrait roughly swaps, where now the this I mean also can be said, colloquially said as like it's a basin of attraction, right, for the global minima. Now you see here, origin falls in the basin of attraction for local minima, right? So if you initialize around 0, you'll get stuck in this local minima line. This is the red line. Okay, so that's for the reason we observed earlier when p plus q is greater than 1 with weight tying. Okay, again, all of this analysis with weight tying, we observe if we do some standard insulation, it's always getting stuck at local minima is precisely because of this reason, and which is confirmed by our flow analysis. And so now you ask, okay, there is a green region as well, right? Like, which is nice, where you can still escape this. So that's exactly what we test here for the full model. Okay. We initialize parameters in this roughly the green region. We see that the purple curve eventually escapes the local minima loss surface and goes to the global minima dotted line. Whereas if you do just the standard initialization around origin, right, the red curve, you get stuck in local minima. So this is for, again, the picture that I'm showing you is for the full model, right? The full single layer transformer without any parameterization or anything. So, but the insights carry over. So, okay. So this shows, knowing where you're initializing can make a big difference. And together, put together, we see that, when p plus q is less than 1, this is how standard initialization takes it to global minima, whereas on the other condition, you get stuck at local minima. Okay. So now you can ask, okay, fine, this is good. But often in practice, we don't know, right, how your input data switching is, right? Is it less than 1 or greater than 1? So luckily here, if you see here, there is a common region of intersection between these two curves, where it's between this yellow asymptotic on the left plot and the yellow asymptote on the right plot. It's like it's like a curved cone. If you initialize in that green region, right, it's a common region for both. We see that the model always goes to a global minima, no matter how your input is, right? If initially in this specific green region, you always go to a global minima. uh, that's like a very cool observation coming from this flow analysis. Okay. And this is all for like a two-dimensional, what do you say, to just with ignoring the attention scalar. And if you add the attention scalar as well, now it's a three-dimensional flow. This is how the flow looks like. Yeah, I agree, it's a bit complicated. That's one of the reason why we started with the two-dimensional. But again, here the main point I want want to focus on is, if p plus q is less than 1, here you see that the set of local minima now is a red plane. Okay, the green sheet that you see here is the set of all global minima. Earlier it was a curve, now it's like a surface. So here you see, if p plus q is less than 1, around origin, it acts like a repelling field, right? That's why you see the arrows going away. So if you do standard initialization, you get to this global minima surface, green surface. Whereas if p plus q is greater than 1, the switching is greater than 1, you see that the origin acts like a, the origin falls in like the basin of attraction for this global minima red surface. So eventually the solutions get trapped there. So similar conclusion as before. Okay. So this is uh, uh, to the answer the other part, which is like how exactly do these models learn the specific patterns, and together, so we now fundamentally address these two questions, right? When you consider first order Markovian inputs with single layer transformers, what exactly do these models learn and how exactly do they learn? So this completes the picture for this setting, through which we saw these main takeaways are, as I said, even surprisingly, the models can fail to learn first order Markov chains, and we saw under what conditions this happens. And in particular, we saw the crucial interplay between Markovian switching, right? We saw less than greater than 1, and also the role of initialization, where you're initializing, play a very, very important role in the overall learning dynamics of the model. Okay, so these are the key takeaways from this part. Okay, so this concludes part 1. Now, gently moving on to part two. So here we consider models that have strictly uh, depth greater than one, okay, and memory could be arbitrary. So here another interesting phenomena emerges that you might all be familiar with, which is in-context learning, okay. So what exactly is in-context learning? So as the name suggests, the main idea is that many of these models exhibit this uh, uh, phenomena where, given like a long sequence of text, the model based on the current context, sorry, if it was to make a prediction, let's say at this point, like after Mrs. Durs, it takes a look at the entire context and see wherever the same context has appeared, and uses the next token preceding them as a proxy to estimate the current one. Okay, so that's like the overall idea for in context learning. Uh, Specifically in the context of Markovian inputs, the idea is that, let's say your last context is this two tokens, 0 and 1. You look in the past wherever it has occurred. So in this case, yeah, in the preceding 2 and 3. So now to predict the next symbol after 0, 1, now you say, okay, it's like a now uniform distribution between 2 and 3, right? Because that's the only instances where it has occurred in the past. Yeah, so main idea is you see wherever the same context xt that you have at the current token has occurred in the past and use it to predict xt plus 1. So mathematically, you can write this in context estimator as the following, right? At any time t, so the next token prediction probability for a symbol x given the context x1 to 2 is, so you look for all the indices I in the past, okay, where the k history xi minus 1 to xi minus k matches the kth history preceding the current token, current context xt. Okay, so this is xt to xt minus k plus 1. So you see wherever this context matching has occurred, and use the token following that, which is xi, as a proxy for your current estimate, and just you normalize it, the standard normalization. So this is the overall idea behind in context estimator. Okay, and so the natural question now is to ask, okay, if you have a kth order memory, yeah, kth order Markov chains, can ask like what's the depth you need to estimate, represent these in context estimators or learn these in context estimators. Okay, that's the natural question here. And the current understanding that we had so far from various existing works is that if you were to capture a kth order Markovian process, some part of your model has to scale, like either number of heads of the model in the model, or like the number of layers, it should scale with k. Okay, so that was like the traditional folklore knowledge. But surprisingly, we found that if you train them for long enough, even like a two-layer transformer can capture, like in this case, like up to order 4, whereas a three-layer model can going all the way up to order 8. Okay, which is like very, very surprising, because order 8 Markov chain is something not a trivial one. It's quite difficult. And so this suggests that there's something interesting going on, much deeper than we thought. And that's exactly the motivation for us to pursue and understand what's happening in this scenario. And the main result that we show here is that, surprisingly, you can show that for any kth order in context estimator that I showed before, it suffices to just have a three-layer transformer, okay, with just one head per layer, and like other standard relative encodings and layer norm, with nothing scaling in k. Okay, it turns out that this is all you need to represent any kth order in context estimator. Okay, and behind this, a crucial part and the role played by these layer norms. Okay, it turns out that if you remove layer norms from this architecture, you can show that you strictly need logarithmic depth to capture this kth order Markov process. Okay, so that's like the main result that we show here. And the main idea behind this construction is that using first two layers, you can capture this, kth order context in a clever way. And the third layer we use is to match wherever this context matching occurs, and then use and do the counting, like as you see in the estimator. So you can show that with three layer, you can realize this such a in context counting estimator. Okay, and in a more recent work, actually we show that you can cut down this three layers to all the way down to two layers. Okay, this is like a recent work that just we put it on archive if you're interested. Turns out that even two layers suffice, but yeah, for the purpose of the talk, let's say we have three layers. And yeah, so this concludes the main question that we have here, like if you have to capture any general kth order process, it turns out that yeah, 3-layer depth is enough, and this concludes this question of what exactly do these models learn in this setting. Okay, but this question hasn't been answered yet, right? Like how exactly do they learn? And this is something that's currently ongoing research, and in fact very challenging, much difficult than the earlier setting, but this is something we believe is tractable, and this is something we are working on. Okay, so together, going back to if you recall, when we started the talk, I said we need principal set of frameworks and tools to fundamentally understand how these models learn, and yeah, what exactly do they learn. And using our framework, right, attention with Markov, I showed how in the context of transformers we can very precisely address this question, thanks to yeah, a principled, like a principled way to look at these models. And uh, yeah, that's what this Markovian setting entailed us, enabled us with this rich representation. Sorry. Yeah. Sorry. Yeah, that's what, using this Markovian structures, we clearly saw how these models learn. But that's not the end of the story. There are, as you know, like Markovians are like one set of tractable models, but that's not the end of the story. There are even more complicated also and more realistic models, such as like HMMs, which could probably even much more deeper insights into what these models could learn. And likewise, we only focus so far on like transformers, but there are also many other interesting set of models that are currently yeah uh, under yeah under implementation under various settings, like for audio processing, genomics. The like it's not just transformers, like SSMs and Mamba that you might have recently heard, that are also under a lot of interest as well. So it would be interesting to study how these models behave under these structured data frameworks. Okay, and so and through our analysis, we saw how the key role of initialization is, and also the input properties, and scaling them to like much bigger, larger scale of models is another interesting direction, where that can give us, that will be even more impactful in terms of how do we train these models, like what components we don't need, like how do we initialize these things. So that's like the another bigger direction one could pursue here. Okay, so with that, I conclude my talk, and yeah, thanks a lot for your interest and attention.
Oh, thanks. Thanks so much for the great talk.
Thank you.